My talk today is application of scanning nonlinear direct electric microscopy for various piezoelectric domain structures. I'm Odagawa from National Institute of Technology, Kumamoto College, Japan. Here is the contents of my talk today. I will show you some measurement method and example. Okay, at first, I will explain the principle of SNDM briefly. Scanning nonlinear dielectric microscopy, called SNDM, was invented by Professor Cho of Tohoku University. It can obtain polarization distribution images with nanometer resolution. Here's the image I measured 20 years ago. A measured sample is PZT thin film. These are the SNDM images, and these are the topography measured by conventional Abraham system. Measured areas 2 micron in this case, and 0.5 micron in this case. We can see a domain structure in one grain like that. We think that we measured AC domain in a grain in this case. SNDM is very useful for the domain distribution measurement like that, like this. Next, I will explain principle of SNDM briefly. This is a relation between electric displacement D and spontaneous polarization P, and direct constant permittivity efficiency 3 and electric field E3. Usually, we consider these two terms in linear region. However, when we consider nonlinearity, it is necessary to consider the nonlinear direct constant here and here, like that. When the polarization direction changed like this way, changed to this way, linear constant epsilon 3 is not changed. However, the sign of odd order nonlinear direct constant changed like this. It means that judging from the sign of nonlinear direct constant, we can determine the polarization direction. Next, I will tell you how we evaluate epsilon 3. Here, we think parallel plate model of a capacitor. The capacitance depends on the dielectric constant epsilon 3. When we apply the electric field between those electrodes, a capacitance of it does not change in linear discussion. However, it does change in nonlinear discussion. Important things is the capacitance change is positive or negative. Yes, it depends on the polarization direction. Okay, here shows a block diagram of SNDM. Important thing is how we measure the small capacitance change by using this LC oscillator. We can measure it. It consists of LC resonator, and probe needle is connected to the LC resonator like this. When the needle contact to the sample, it composes a capacitor, which value depends on the dielectric constant of the substrate. Okay, we apply the electric field between the sample stage and the probe tip to generate the nonlinear effect. By detecting the frequency change by FM demodulator and locking amplifier, we evaluate the capacitance change with applying the electric voltage. This is a block diagram. Next, I will show you measurement of layered thin film. Okay, I made a talk about this topic 2 years ago in this symposium, so I explain briefly. Conventional SNDM measure the structure like those. On the other hand, I try to measure such a layered structure. Usually, it is difficult to fabricate those structures. However, Professor Yanagitani of Waseda University fabricate these structures by controlling the sputtering condition. I believe that this technique is very important for MEMS devices applications. However, to measure this structure, we must cut the sample and polish it and then measure the cross-section of it if we use the existing method. Therefore, I have developed to measure the layer structure from the surface non-destructively. Principle of this measurement is simple. When we measure this polarity, I assume that the SNDM output is +1. In this case, when we measure the opposite polarity, output should be -1. Now if we measure the layered structure, the output signal will be between +1 to -1, which depends on the thickness of the inverted layer. Therefore, by measuring the output signal precisely, we can determine the thickness of the layer. We have obtained the method of quantitative measurement of the layer thickness as shown in this slide. But I don't have enough time today, so I will skip this. Here is the experimental result. We measured scandium-doped ALN. The structure is here. Okay, we get the value of 1.33 micron by this method. This value is almost same as the actual value. Feature of this measurement is we can measure the distribution of the thickness like that. Next, I will show you the measurement of the lateral polarization. In the vertical polarity measurement, electric field for measuring capacitance and the electric field for generate nonlinear effect are same direction, like that. On the other hand, in lateral polarity measurement, the electric field, this and this are orthogonal. For the lateral measurement, we put additional electrode like this to add the electric field parallel to the surface. We fabricated such kind of electrode. Electric field this way and this way has a 90-degree phase differences. So we can obtain a rotating electric field. When the direction of electric field is parallel to the polarization, output is maximum value. So we can determine the direction of the polarization from the phase output of the locking amplifier. Here shows the experimental result of BNT piezoelectric ceramics. These images are measured from the sample before pouring, and these two images obtained from the sample after pouring. Clearly, we can see that by the pouring process, polarization are aligned like that. We can get such large domains. In this case, we don't have any domains, and we get the domains by pouring. And this domain has a polarization direction of this, and this red region have the polarization like that. Okay, next I will show you domain motion measurement. A motivation of the development of the measurement system is shown here. As you know that piezoelectric property in ceramics depends on domain dynamics. A static property is not equal to the dynamic property, especially in large amplitude drive. Okay, so therefore, it is necessary to develop domain measurement system in motion for the development of the materials. Here shows a measurement system. This is a conventional SNDM, and we add the additional oscillator to drive sample devices or materials. In each point on the scanning, we stored the output signal with applying the electric voltage, drive voltage. After the measurement, we sort the data, and we can obtain the domain behavior over the time. Here shows the data sorting. At each point, we collect the output signal. At point A, we get those data and move to the next point of B. At the point B, we also measure those data and then move to C, and we get those data. And after the measurement and after the acquisition of all data, we sort these data with the time. So we get the polarization distribution over the time. Here is one measured result. Sample is piezoelectric ceramics near MPB. We applied electric voltage like that. The frequency is 1 Hz. Okay, in each time, we measure the amplitude signal and the phase signal of SNDM. Okay, interpretation of this result is still under consideration, but I'm thinking that this kind of phenomenon may have occurred. In this region, the sample is rhombohedral phase, and this region, a sample is tetragonal phase. As electric field increasing, and the phase switched near here, and sign of the SMD signal switches from this and this, like that. And then electric field reduced and become negative. The phase changed around the around the head again. Like this interpretation is still under consideration. Okay, next I will show you the piezoelectricity distribution measurement. The reason why we need to measure the piezoelectric distribution is as follows. Microscopic piezoelectric constant D33 is not uniform, especially in ceramics and thin films. As I showed at the beginning of this presentation, one grain may have the domains. Of course, it must reduce the piezoelectricity. Conventional measurement method like D33 meter and resonance resonance method measure only the average value in measured area. To develop large piezoelectric materials, I think microscopic analysis is important. Moreover, polarity inversion cannot be measured by the X-ray diffraction, so we try to develop this kind of a system. I will show you how to measure the microscopic D33. There are constitutive piezoelectric equations. To determine the D33, we simply measure the strain with applying the electric field. However, the displacement which causes the strain is very small. In case of PZT, the value is relatively large. But in case of the LN or other materials which are used in high-frequency devices, the displacement is very small. To measure this small displacement, SNDM system can be used. Probe needle doesn't contact the sample surface in this measurement, and the sample surface is coated by the metal thin films. The capacitance between the tip and the surface changed by the displacement. The distance changed, capacitance changed. So we can determine the displacement from the output signal of the SNDM. This is a relation between output signal and distance. This is oscillation frequency. As changing the distance, the frequency decreases. On the other hand, output signal increases rapidly. Unit of the lateral axis is micrometers. So if we use the output signal, we can detect the very small displacement. This is an experimental result. Sample is PZT ceramics and measured area is 100 micron square. As shown in this image, distribution of the piezoelectricity is measured. In summary, I described several measurement techniques to measure the piezoelectric domains, like that. I would like to acknowledge this person. Thank you very much.